Of course, there are some other fine-tune process that I will not talk about here. But then if we can figure out how to make a pi pulse, then basically we can start to and then to optimize the half pi pulse and those things. And then we go through all XY steps there, and we try all different combinations of single qubit operations, and then hopefully that we can fine-tune those power and frequencies and to get this a nice fitting to the expected curve. And then once this is done, then we can do a randomized benchmarking and then to get a good gate fidelity. And this is so far what we can get in the best case, 99.86 for native XY gates. And yeah, so and then we can move forward to swap spectroscopy. There we can swap the qubit state between qubit 1 and qubit 2, and then so between 1, 0 and 2, 0, 1. And so this is how the swap spectroscopy looks like. So horizontal axis is we tune the coupling, the coupling between the coupling pulse height and the amplitude, and then the length, and there we can get this. And then of course the same thing can be done on the case where 2 qubits are all in the excitatory state, and then we can swap it to 2-0 state, and then this that gives us these structures. And so otherwise basically they are pretty much the same. And then with this we can go further to control phase gate, and then that means if we have qubit 0, the control qubit, that we can place that into a 0 state or in a 1 state. And then in these two cases, then we look on the second qubit we call target qubit, and then how its phase changes. So if the control qubit is placed in a ground state, then we expect that the target qubit doesn't have a phase change. Whereas if we put the control qubit to the excitatory state, then we see it rotate by 180 degrees. And with a very, very careful tuning, and then finally experimentally we get a phase difference of 177.7 degrees. Of course, this changes every day, I would say. And then also the amplitudes and for the corresponding phase changes and of the qubit, the target qubit, and then we hope that the amplitude for the two cases where the control qubit is 0 or 1, that they give us the same height. Okay, so of course there are a lot of small details but very tedious work that we have to do to optimize Z-gate, to optimize this Z-gate shape and heights. And so so we go through a scan of the Z-gate height, and then try to see the best Z-gate values that we should apply. And then finally, there is something that we have to consider, that in reality, at the room temperature, we have AWG arbitrary waveform that suppose that it gives us this square wave. But at the low temperature, mini-Kelvin temperature, actually qubit may see a shape looks like this. And so that has to go through a calibration where we use a qubit as the probe, and then we can see that qubit actually shows this the curve, the pulse that its receiver looks like this. And so with some fine tuning on the AWG curves and the shape of AWG curves through equations, then we can finally modify it so that qubit sees this curve instead. And with this, we can, the result is that before fine tuning, we see the CZ chevron plot looks like this, but with without fine tuning, then we can finally make the symmetry and looks better. Okay, so with all this, and then we can work on the, then we can achieve a Bell status. Of course, it's not ideal, but yet we can see clearly that the population on 0, 0, and 1, 1 state, they are at the maxima. And these two are just imaginary parts. Okay, so now suppose we have 5 qubits and they are connected in 1D array, and so they are, so what we have to do to bring this system up is first we find out the maximum qubit frequency of each qubit, and very unfortunately, our laboratories can still lack of a very good control of the qubit frequencies. So this may spread randomly everywhere, and with a very wide spread, I would say. And then, but with these given values, what we have to do is we first need to find out the idle frequencies of each qubit. And then after that, we also need to find out the control phase CZ gates and frequency of each pairs, say between Q0 and Q1, and Q1 and Q2, Q2 and Q3, Q3 and Q4s, and those pairs, and we need to identify those operation frequencies. And so what to do here is we to find out idle frequencies, that for a given maximum frequencies, and for the 5 qubits, first we find out, we write down a cost function, and this cost function contains 2 terms. The first term is ZZ interaction, and the second term is the coherent, is that accounts for the coherence limiters of each qubit gates error. Okay, and so in the first term, that this ZZ interaction that has that we count as the between neighboring qubits and between the next nearest qubits. Okay, so and this ZZ interaction is written here, and so that gives us this number eta, and then eta is given taken from this equation that yeah, the second term is that account for decoherence is because we have in a given in finite in a flux case, in a case of flux present of flux, then there is a flux noise, and then that has to be accounted for, and then so that's also written here, and so with all this, we can get a set of 5 qubit idle frequencies, and then to find out CZ operation frequency, we have to again there is a cost function, and again there are 2 terms. The first term is the qubit operate the ZZ interaction, and the second term is the coherence limit of CZ gate. And so in the ZZ interaction, of course, when during CZ interaction, during this operation, we put that separate by charging energy of the idle qubit idle. Then this function is written here, and then So again, there is an equation that describes this decoherence in this case. And so apply these equations, then we can get this value, and then also the